Okay, so we just learned how to identify or to determine the definiteness of a matrix, in particular a real symmetric matrix, by looking at the eigenvalues. Okay, but there's another way to determine the definiteness of a matrix without computing for the eigenvalues, but we need to learn some concepts. The first we need to learn in order to determine the definiteness of a real symmetric matrix is the concept of a principal minor. Okay, so A is an n by n matrix. Okay, the submatrix obtained by deleting any n minus r rows. Okay, so n is the order of the matrix. Okay, of the square matrix. So if A is a 3 by 3 matrix, then n is the order, so n equals to 3, right? If you delete n minus r rows and the same numbered columns, later we'll see an example of how to actually do this, but this is the definition. It's called the principal submatrix of order R, and its determinant is called the principal minor of order R. Okay? So for example, you have this 3 by 3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so you have this matrix. Okay, now let's um, obtain the principal submatrix. Okay, principal submatrix of order 1. Okay, so R in this case is 1, order 1. So what does the definition say? The definition says that that principal submatrix is obtained by deleting any n minus r rows and the same number of columns. Okay, so what is n minus r in this case? N is the order, it's 3. So n minus r, okay, the uh, the order that we want to uh, look for, okay, the submatrices, the principal submatrices that we're looking for is of order 1. Okay, so what we'll do is we'll delete n minus r rows and columns. So n is the dimension of the matrix. So it's 3 minus 1, which is r. So we'll delete 2 rows and columns. Okay, but not just any particular row and column. It must be of the same number. Okay, so what are the principles of matrix of order 1? Okay, let's just write this one out. A12, A13, A21, A22, A23, and A31, A32, A33. Okay, great. That's this matrix A. Now we will delete the same numbered row and column. Okay, we'll delete 2 of them. So if we delete the first row and the second row, we should also delete the first column and second column. Okay, so one principal submatrix of order 1 of A is the matrix A33. Okay, so that's one principal submatrix of order 1, but it's not the only one. Okay, so another principal submatrix of order 1 is, let's just write this matrix again. A31, A32, A33. Okay, that is this matrix. So in the first case, when we got A33, over here we deleted the first row and the second row and the first column and the second column. Now, let us delete the first row and the third row, okay, and the same numbered column. So first column and third column. And so another principles of matrix of order 1 is A, 2, 2. Okay? And we have one more. Okay? We have one more. So the other principles of matrix of order 1 is what? I guess you know by now. So let's write it again. A31, A32, A33. When we got this one, we deleted first row, second row, and first column, second column. When we got this A22, we deleted first row, third row, and first column, third column. Okay. Now, I guess you know what the next one is. You delete the second column and the second row and third row, and the same number, second column and third column. Okay, it's same numbered rows and columns. So another principles of matrix of order 1 is A11. Okay, and those are the principles of matrices of order 1 of A, of matrix A. Good. Now, what about principle? Let's just, where will we put this? Let's just put this here. How about principles of matrices of order 2? Okay, so what does the definition say? The definition says that this is the order, this is the R, okay, 2. We must delete n minus R, so it's 3 minus 2. We should delete one row and one column, and it's the same number. Okay, so again, this is A11, A12, A13, A21, A22, A23, A31, A32, A33. This is the matrix A. Now we will delete one row and one column uh, the of the same number. Okay, same number. So if we delete row 1, we must also delete column 1. Okay, so what's the submatrix obtained there? Well, the submatrix obtained there is A22, A23, A31, A32, and A33. Okay, so that's one principal submatrix of order 2. Let's look for another one. Okay, what's another one? In the previous case, we deleted row 1 and column 1. Now let's delete row 2 and same numbered column 2. Okay, so another principal submatrix would be A11, A13, A31, A33. Okay, good. That's another one. And there's one more. Okay, there's one more. I guess you know it by now. A22. This is A22. To obtain this one, we deleted the first row and first column. This one, we deleted the second row and second column. Okay, keep in mind it's the same number. Okay, of course the other one is when we delete the third row and the third column. Okay, so the last principal submatrix of order 2 is A11, A12, A21, A22. Okay, great. Those are the principles of matrices of order 2. Okay, great. Now the question is, what is the principal submatrix of order 3? Okay, this is the last one. Now according to the definition, we should delete n minus r, same numbered rows and columns. Okay, n minus r. But in this case, r equals to 3, so n, which is 3, okay, which is the order of the matrix A, is 3 minus r 3 equals to 0. So we shouldn't delete any row nor column. So we're left with the matrix itself. So the principal submatrix of order 3 is this matrix. Okay, great. Okay, so you now know how to get the principal submatrix of order R. Now, the next question is, what is the principal minor of order R? Well, the principal minor is simply the determinant of the matrix. Okay, so for order 1, it's simple. The determinant of these matrices is the number itself. Okay, so for this matrix, the determinant that 33 A33 is A33. Okay, and so on and so forth. So that's the principal minor associated with this matrix, and this matrix. Okay, for principal submatrices of order 2, the way to get the minor is to multiply the diagonal and uh, subtract the off diagonal, the product of the off diagonal. You know how to do that. You know how to get the minor of the determinant of a 2 by 2 matrix. Okay, so that's a determinant. And then finally, the determinant of this matrix is the principal minor of order 3. Okay, now there's another principal submatrix that we need to learn. It's called the leading principal submatrix. Okay, now the leading principal submatrix is just a subset of the principal submatrices. Okay, the principal submatrix is obtained how? The principal submatrix of order R is obtained by deleting the last n minus r rows and the last n minus r columns. Okay, in the previous discussion where we discussed principles of matrices, it's the same numbered rows and columns. Okay, now it's the last n minus r row and the last n minus r columns. We'll show this later. Okay, and the determinant of that leading principal submatrix is called the leading principal minor. Okay, so let's again go to the example. A, which is a square matrix of order 3. Again, let's do this. A1, 2, A1, 3, A2, 1, A2, 2, A2, 3, A3, 1, A3, 2, A3, 3. Okay, now let's look for the leading principal submatrix of order 1. Okay, now what does the definition say? The definition says that we have to delete n minus r, the last n minus r rows, and n minus r columns. So what's n minus r in this case? N is the order of the matrix A, which is 3, and r is the order of the leading principal submatrix, which is 1. Okay, so we would delete the last 2 rows and 2 columns. Okay, so in this case, when we delete the last 2 rows, so first row, the last 2 rows are row 2 and row 3, right? So let's delete row 2 and row 3. Okay, and the last 2 columns, which is column 2 and column 3. So therefore, the leading principal submatrix of order 1 is the matrix A11. Okay, now what is the leading principal submatrix of order 2? Okay, so let's erase these lines. Okay, so let's draw it again. A1, 2, A1, 3, A2, 2, A2, 3, and A3, 2, A3. Okay, great. We're tasked to find the leading principal submatrix of order 2. So according to the definition, we should delete the last n minus r row. So it's 3 minus, the order is 2, the last the last one row or the last row and column. Okay, so by that definition, we should delete the last row, which is row 3, and the last column, which is column 3 of this matrix A. So you're left with A11, A12, A21, A22. This is the leading principal submatrix of order 2. And the leading principal submatrix of order 3, well, in this example, n minus r is equal to 3 minus 3 equals to 0. We won't delete anything. So the leading principal submatrix of order 3 is the matrix itself. Okay? 1, 3, A 2, 1, A 2, 2, A 2, 3, A 3, 1, A 3, 2, A 3, 3. Okay? So these three are the leading principal submatrices. Now, notice that these are subsets of the principal submatrices. Okay? There are more principal submatrices than the leading principal submatrices. Okay? Great. And so the determinant of these matrices are the leading principal minors. Okay, so the leading principal minor is of order 1 is the determinant of this matrix, which is simply that A11 is equal to A11. Okay, so that's a leading principal minor of order 1. Okay, what is the leading principal minor of order 2? Well, it's simply this, the determinant of this matrix, so it's A11, A22 minus A21, A2, A12. Okay, so that's the leading principal minor. And the leading principal minor of order 3 is the determinant of this matrix. Okay, so uh, don't be confused. Um, the principal submatrices are obtained by deleting the same numbered row and column. Okay, while the leading principal submatrices are obtained by deleting the last n minus r columns and rows. Okay. Okay, so now let's go to an example. So the matrix A in this case is 3, 0, 4, 1, 1, 2, 1, negative 2, 2. Okay, so this is matrix A. Now, how to get the principal minors of this matrix? Now, first, let's go to principal minor of order 2. Okay, so how do you get the principal minor of order 2? I mean, principal submatrices of order 2. You must delete since the order of this one is 3, you must delete 3 minus r, which is 2, equals to 1, 1 um, row and column, which is of the same number. So the first one is when you delete row 1 and column 1. Okay, same number, 1 and 1. And the first principal submatrix is this one, 1, 1, 2, negative 2, 2. Okay, now let's delete row 2 and column 2. Okay, same number, 2, 2. Then we're left with the matrix submatrix 3, 4, 1, 2, which is this one. Okay, and this is another submatrix of principal submatrix of order 2. And the last one is when we delete row 3 and column 3, you're left with the submatrix 3011, which is this entries. And so that is the final uh, principal submatrix of order 2. Okay, now let's get the principal submatrices of order 1. Okay, so in this case, you'll delete n minus r is equal to 3 minus order 1 is 1, 2 rows and 2 columns which are of the same number. Okay, so the first case is when we delete row 1 and row 2. That's the two columns. But we also must, I mean 2 rows, but we also must delete the same numbered column. So if we delete row 1 and row 2, we must delete column 1 and column 2. So you're left with the submatrix 2. Okay? If we delete first row and third row, we must also delete the first column and third column. You're left with the submatrix 1. And then finally, if we delete the second row and the third row, we must also delete the second column and the third column. We're left with the submatrix, principal submatrix of order 1, another one, 3. Okay? So that's how you get the principal submatrices of order 1. And like we have shown before, the principal submatrix of order 3 is the matrix A itself. We're not deleting since R is 3, we should delete n minus R 3 minus 3, which is 0. We're not deleting any row or column. That's why we're left with the matrix A itself. Now, to get the leading principal submatrices, okay, for order 1, okay, for order 1, you must delete the last 3 minus 1, the last 2 rows and 2 columns. Okay, so when we delete the last 2 rows, so row 2 and 3, and the last 2 columns, column 2 and 3, we're left with the matrix 3, okay, which is the leading principal submatrix of order 1. Okay, now to get the leading principal submatrix of order 2, we must delete the last n minus r, 3 minus 2 equals to 1. We must delete the last column and the last row. So in that case, when we delete the last row and last column, we're left with this matrix. So that's the leading principal submatrix of order 2. Okay? And then finally, the leading principal submatrix of order 3, because we're not deleting anything, n minus r equals to 3 minus 3 equals to 0. We're not deleting anything. It's the matrix A itself. Okay? So notice that these are also elements of the principal submatrices. Okay? And these are called the leading principal submatrices. Leading. Now, this next theorem is determining the definiteness of a matrix, in particular, a real symmetric matrix using principal minors and leading principal minors. The previous theorem that we had was that you can determine the definiteness of a real symmetric matrix A by looking at the sign of the eigenvalues. Okay, so if you don't want to compute for eigenvalues, this theorem will come in handy. Okay, so the theorem says, take note, this will only be valid, or this will only work if your matrix A is a real symmetric matrix. Okay, so this is key. This theorem will only apply to real symmetric matrices. Again, just to review, what is a symmetric matrix? A symmetric matrix is the matrix where its transpose is equal to itself. Okay, and the real there pertains to the fact that the entries in that matrix are real numbers. Okay, great. So what does the theorem say? The theorem says that A is positive semi-definite if and only if all its principal minors are non-negative. What does non-negative mean? It can either be 0 or positive. Okay? All the principal minors of matrix A. Okay? If that's true, then it's positive semi-definite. It's negative semi-definite, okay, if and only if its principal minors of order 1 are non-positive, meaning either negative or 0. Those of order 2 are non-negative, okay, so it can either be positive or 0. Those of order 3 are non-positive, and so on and so forth. So they're kind of like flipping signs. Now, Again, what's a principal minor? Principal minor is just simply the determinant of the principal submatrix. Of the method to which we find them were discussed just previously. Okay. Okay, so that's positive semi-definite and negative semi-definite. Now, A is positive definite if and only if it's leading principal minors. Okay, now we're talking about leading principal minors. Okay, what again is a leading principal minor? It's simply the determinant of the leading principal submatrices. Okay, it's leading principal minors. All the leading principal minors are positive. Okay, okay, great. And it's negative definite if the leading principal minors, if and only if the leading principal minors of order 1 is negative, order 2 is positive. Okay, so it switches sign when you go from order 1 to order 2. And then order 3 is negative, so it switches sign again, and so on and so forth. Okay, so this theorem says that if you have a real symmetric matrix A, an alternative to finding the eigenvalues, the sign of the eigenvalues, is just to look at the principal minors and the leading principal minors. Now, here's an example. This matrix A over here is a 3 by 3 matrix. First, why can we use the theorem? Well, the entries are real numbers. Okay, these entries are real numbers. And what's the most important thing? It should be a symmetric matrix. Okay, so we can use the theorem because it's a symmetric matrix. How do we know that? Well, we get the transpose of A. We'll make the first row the first column. So 3, negative 2, 0. The second row, the second column, negative 2, 3, 0. And the third row, the third column, 0, 0, 5. Notice that this is the same matrix as A. So therefore, this matrix A is symmetric. Now, therefore, we can use the theorem, okay, for that we just described earlier, uh, which deals with looking at the principal minors and leading principal minors to determine the definiteness of the matrix. Okay, great. Now, the question is the matrix A positive definite? What is the what does the theorem say? So A, the real symmetric matrix A is positive definite if and only if the leading principal minors are all positive. Okay? Now, how do we get the leading principal minors? So the principal minor of order 1, let's go to the principal submatrix first of order 1. Okay? So we'll to find that, we'll delete the last two rows and two columns. So it's this one, this one. Okay, so it's this matrix 3. So the determinant of 3 is simply 3. Okay, so this is order 1. The next is, how do we find uh, the leading principles of matrix of order 2? Okay, so we must delete the last 3 minus 2, 1, the last row and column. So let's delete the last row and column here. You're left with the submatrix 3, negative 2, negative 2, 3. Okay, now to get the determinant, you simply have to multiply this. It's 9 minus negative 2 times 2. Negative 2 times negative 2, it's positive 4. So 9 minus 4 is equal to 5, which is this one. Okay, great. This is the leading principal minor of order 2. Okay, and the leading principal minor of order 3. Okay, so how do you get that? Well, let's use this last row because it's easy. So we'll just find the cofactor associated with 5 with this entry over here, 5. So let's delete this row and column. So we have 3, negative 2, negative 2, 3. That minor is 9 minus positive 4 is equal to 5. So the determinant of that is equal to 5. Okay? The cofactor associated with that is the cofactor associated with, let's erase this for a moment. The cofactor associated with the element with the entry 3, 3 is just negative 1, 3 plus 3, 6 times 5. Okay? So that's positive 5. Okay? So the determinant of this matrix is 0 times cofactor of C13, C31, plus 0 cofactor associated with C32 plus 5 times C33, which is equal to 5. So therefore, this is equal to 25. Okay, so 25 is the same as this 25 over here. Okay, so now we have found all leading principal minors of this matrix A. So what do you notice? The first principal minor is 3, it's positive. The second principal minor, leading principal minor of order 2 is 5, which is positive also. And the leading principal minor of order 3 is 25, also positive. So what does the theorem say? When all the leading principal minors are positive, then the matrix is positive definite. Okay, great, great. Okay, so let's go to another example. Let's go to another matrix. This matrix A is also symmetric. Okay, you can verify that because the transpose of A is equal to, the first row is becomes the first column 1, negative 1, negative 1. The second row is negative 1, 2, 4. Then the third row in A is now the third column 1, 4, 10. It's equal to the matrix A. So this is a symmetric matrix, and therefore we can use the theorem to establish the definiteness of this matrix. Okay. Now the question is it positive definite? Again, you get the leading principal submatrices. First of order 1, you delete the last 2 rows and 2 columns. You're left with this matrix 1, the determinant of which is 1. Okay. And for order 2, you delete the last row and last column. Okay. And the submatrix that is left is this matrix 1, negative 1, negative 1, 2. This matrix over here, the determinant of that is 2 minus positive 1 is equal to 1. So it's positive so far. Now the leading principal submatrix of order 3 is the matrix itself. Okay, so I'm not showing this, but take it on faith. You can practice. The determinant of this matrix is equal to 0. Okay, so what does the theorem say? If matrix A, a real symmetric matrix A, is positive definite, then all the leading principal minors should be positive. In this case, it's not, because we have a leading principal minor that's 0. So therefore, A is not positive definite. Okay. Now the question is, on the other hand, is it positive semi-definite? Okay. So what is the definition of a positive semi-definite? What does the theorem say in order for you to determine whether a real symmetric matrix A is positive semi-definite? You look at all the principal uh, minors. Okay, so you look at all the principal minors, and if they are all non-negative, meaning if it's equal to 0 or it's positive, then the matrix is positive semi-definite. Okay, now again, this is a little bit more involved because we're now looking for all principal submatrices. Okay, so of order 1, the principal submatrices of order 1, so we must delete n minus r. We must delete 2 rows and 2 columns, which are of the same number. So the first one is when we delete first row, first column. First row, second row, and first column, second column. we're left with the matrix 10. Okay, and then we must delete, when we delete the column of row 1 and row 3, and column 1 and column 3, we're left with the matrix 2. Okay, and then finally, when we delete row 2 and row 3 and column 2 and column 3, we're left with the matrix 1. Now the determinant of this matrix, so that the determinant of this matrix is equal to 10, 2, and 1. Okay, they're all positive so far. Now let's look at the principles of matrices of order 2. Okay? Now how do you do that? Well, you delete one row and one column that is of the same number. Okay, so first let's delete row 1 and column 1. So we're left with the matrix 2, 4, 4, 10. Okay, and then next one, when we delete column 2, row 2, and also column 2, same number. Okay, we're left with 1, negative 1, negative 1, 10. Okay, and then finally, when we delete row 3 and column 3, we're left with 1, negative 1, negative 1, 2. Okay, so these are the principles of matrices of order 2. Now, the principal minors is just the determinant of this matrices. Okay, what are the determinants of this one? This one is 2 times 10, it's 20 minus 16 is equal to 4. Okay, the principal minor of this matrix is the determinant of this matrix. So it's 10 minus positive 1, it's 9. Okay, and then finally we have 2 minus positive 1, so it's 1. Okay, so far we all have positive numbers. Okay, so the principles of matrix of order 3 is the matrix itself. Okay, it's the matrix itself. This is 1, negative 1, negative 1, negative 1, 2, 4, negative 1, 4, 10. Okay, and then the determinant of that, as we have seen in the previous slide. Okay, so the determinant of this matrix, this 3 by 3 matrix, is equal to 0. Okay, so let's go. Yeah, just take it on faith. Okay, yeah, you can compute it by yourself. I wouldn't argue with that. But here, we find that the determinant is equal to 0. Great. So all the principal minors are the principal minors are 10, 2, 1, 4, 9, 1, and 0. They are all non-negative. Okay, they're either 0 or positive. Now, since they are all non-negative, all the principal minors are non-negative, then matrix A is positive, semi-definite, definite. Okay, but as we have shown in the previous slide, it's not positive definite. So it's positive semi-definite, but not positive definite. Okay, so what's the beauty of this thing if you uh, try to condense the lesson? Is remember you have quadratic forms with matrices A, for example, that uh, are not necessarily symmetric. Okay, so how do you determine the definiteness of the quadratic form? Well, what you can do is to convert the matrix A into a symmetric matrix. Okay, and the beauty of the symmetric matrix is that you can use this theorem, provided that they have real numbers as entries. You can use the theorems either by looking at the eigenvalues or either looking at the principal minors and leading principal minors to determine the definiteness of the quadratic form. Remember that when you convert a non-symmetric matrix to a symmetric matrix via the formula 1/2 times matrix A plus the transpose, it will generate the same quadratic form. Okay, so that's the beauty of it. That's why the symmetric matrix has beautiful properties, because you can use, for example, this theorem over here. Okay, so that concludes this part of the lesson.